Say a few words about him. He was one of the founders of KIAS, the Korea Institute for Advanced Study, which was established in 1996, 14 years ago. And then he was the acting director for more than a year. And then he served as a vice president for 8 years till 2005. And after his resignation, I took his office for 2 years. And then he finally became the president of KIAS 2005, and he served 3 years very enthusiastically. But unfortunately, he passed away February, about 4 months shy from the completion of his term. I miss him very much, and to me, he was great motivator, motivating himself as well as many people around him. And also, he was a dreamer and a fighter. So he always dreamed of a world-class institution out of KIAS, and he fights against any art for the stability of KIAS and for the prosperity of KIAS. So we all owe him very much. And also he was a great supporter of this KWMS, Korean Women in Mathematical Sciences. So this tradition should go on. So today I'd like to talk about one of my works I have been doing in KIAS since I joined the faculty of KIAS 10 years ago. And this is one topic, and the other topic could be a circle action on other dimensional sphere, what they call Montgomery-Young problem. It could be very related to your talk, but I think I should correct topic. Yeah, trying to disjoint from previous talk. I do really hope to produce more interesting mathematical work in the near future, and also make a contribution to KIAS, so that I can proudly present to him for many more years to come. Okay, let me begin my talk. So this is all about automorphism groups of algebraic surfaces, mostly, particularly K3 surfaces. And also, in the meantime, I mentioned some relation with combinatorics of Leech lattice or multi-groups. Well, as a geometer, I think the concept of group dates back to Plato's time. It was conceived by ancient geometers. Officially, the concept of group was invented by Galois, but this is geometer's view is different, because the group of symmetries of the geometric objects, such as regular n-gon, platonic solid, circle, and sphere, these geometric objects have many symmetries. So most symmetric object among its class, like regular n-gon, has most symmetry among all n-gons. Like platonic solid has most symmetry among the solid of same number of faces, and so on. So the symmetry group in this case means that for regular n-gon, it is a dihedral group, and platonic solid, that is a polyhedral group. And circle, in this case, a rotation group extended by a deflection, and sphere, and so on. So these groups are quite well known and quite classical subject. And then, as you know, that Descartes invented the coordinate system, and then the algebra, the equation, suddenly become an interesting geometric object. The set of solutions become a geometric object called algebraic variety. So what kind of symmetry one can think of for algebraic variety? So the question is, what if the geometric object X is defined by a system of polynomial equations? So in this case, a correct notion of a symmetry is a rational self-map with an inverse of the same kind. So here, rational means the rational function with coefficient in K. K is the ground field, and defining the variety, and the coefficient of polynomial. So for simplicity, for convenience, let's assume the field K is algebraically closed. For example, the field of complex numbers. And these symmetries are called K birational automorphism, or simply birational automorphism if the field K is clear from the context. And these birational automorphisms form a group because you can compose two birational automorphisms, and then you get another birational automorphism, and you can think of the inverse. So I denote this one is birational automorphism B or K of X. If X and Y are birational, then their groups are isomorphic, and the converse is also true. And then we may assume X is projective and non-singular. So projective, simply if you have affine variety, it's just a solution of polynomials, and then you can embed this variety into a projective space, or you can homogenize the defining equations by adding one more variable. Then you can get the projective variety, which is a compactification of the given variety. And this birational automorphism, this notion is invariant under this compactification. So you can think of the given affine variety, or you can think of its compactification, projective compactification. And also, you can think of its non-singular resolution, a resolution of a given variety. Usually, the given variety is singular. Yeah, sometimes the problem is quite easy. So this is due to Hiraka's celebrated theorem on resolution of singularity. So this is always true in characteristic zero, and this resolution of singularity is still open in positive characteristic. This is true in small dimension 2. But higher dimensions, this is still wide open, and Professor Hiraka announced a proof a year ago or 2 years ago, but it turns out that it's not quite substantial. So he took it back for the moment. And so anyway, so in this case, the group of birational automorphisms is equal to the automorphism group of the field, the function field, This is the field of rational functions on X. So this is really, I mean, studying this group is nothing but studying automorphism group of this function field. So in general, it is a highly non-trivial problem to determine this group, even if X is defined by a simple-looking equation. For example, this is quadratic, this is a degree 4 equation in affine, three-dimensional affine space. So if you add one variable x3 or x0, then you can homogenize this equation like this. So this is compactification of this affine variety. So this is projective variety, happen to be a K3 surface. Well, if you think of only linear change of coordinates, then you can compute the automorphism group rather easily. And this is rather elementary. But if you think of rational change of variables, change of variables by rational functions, it is kind of deadly hard problem. But when, for example, if you try to solve the differential equation, then you usually change the equation by plugging rational parameterization or rational change of variables. So the rational change of variables is more natural than linear change of variables. So let's think of the case, simply the affine space. So you can think of this one as a variety without any equation, or just one linear equation in one-dimensional higher space. And in this case, the group has a classical name called the Keum group of degree n. I'm sorry, let's go quickly moving. Okay. So one-dimensional case is quite well known. In this case, in one-dimensional case, birational notion and just biregular notion are the same. And in this case, this is nothing but a projected by general linear group. And this is 2 by 2 matrix modulo centralizer. The diagonal matrices. Scalar matrices. And these are nothing but all Möbius transformation mapping the complex number Z to AZ plus. So this is what we call linear fractional or bilinear transformation. So A, B, C, D here correspond to a matrix belonging to this group. And this is nothing but the automorphism group of function field, with one variable Z. And all finite subgroups of this group were classified. This is a classical result. They are all cyclic or polyhedral. And in dimension 2 case, this one has a long history. Max Netter, the famous female mathematician Annie Netter, was the daughter of Max Netter. And he proved that this group must be generated by linear automorphisms, linear automorphisms, and one more involution, sigma, is a standard Keum transformation, which maps x, y, z is a projective coordinate. This maps to like this, 1 over x, 1 over y, 1 over z. Well, Max Netter, when he announced his proof, so one of the audience raised a hand and claimed that the proof was wrong. And then he burst into tears. So he thought that this was his best work in his life. So finite subgroups of this group are quite recently classified. There's many people worked on this, like Beauville, and some involutions have classical names like Bertini involutions and the Jonghae involutions and so on. And at the dimension 3, then nothing is known. So we don't know what kind of generators we need to express this group, or we don't know whether it is simple what we even don't know, no, it's simple. We know that this group is not normal subgroup. The linear group is not normal subgroup inside here. So here's a natural question. For given general X, how to compute this group? So before computing, can we determine whether it is finite or not? For example, classify all X with this group is finite. In one-dimensional case, the finiteness can be determined by the genus of the variety. So in this case, it is a Riemann surface of genus G. If the genus is bigger than or equal to 2, then always finite. Otherwise, it's always infinite. And if in dimension 2 case, in principle, we have the same result. Finiteness can be determined in principle. It depends on analytic classification of algebraic surfaces, 1950s, or its generalization by Godaya to complex surfaces. Well, this is I think this is one of the major achievements in 20th century mathematics. So given equations, then you can determine the dimension. If the dimension is 2, then you can still work on the surface, and then you can get, for example, in some way you can determine that whether the given surface is general type, for example, and then you don't need to worry about just general type, and always this group must be finite. So general type has very small number of bidirectional automorphisms. If X has Godaya dimension negative, then this group is always infinite, like this. So we have more, but in between, the most interesting case, K3 is, X is a K3 surface case. K3 surface is not general type, it has Godaya dimension 0, so it's just kind of in between. So automorphism point of view, K3 surface is most interesting. In this case, bidirectional automorphism group is equal to the biradial automorphism group, and it is always a discrete group. It could be finite or it could be infinite, depending on the K3 surface. So what is the K3 surface? It can be characterized by two properties. The two-dimensional homomorphic cotangent bundle is trivial, or the tangent bundle and cotangent bundle are isomorphic, or there is a nowhere vanishing regular 2 form omega x on x. So this in the global section of this of this bundle is one-dimensional, generated by this omega x. But on the other hand, there is no global 1 form. So irregularity should be 0. So K3 is a two-dimensional analog of an elliptic curve, and higher dimensional analogs of K3 are Calabi-Yau manifold and hyperkähler manifold. Both are quite intensively studied. Well, nowadays the people working on K3 surfaces have a goal that for elliptic curves, we have very precise and very rich theory, arithmetic and geometry both. But K3 surfaces, it's much more complicated, but we don't have much, we don't have as much information on arithmetic of K3 surface as we do have for elliptic curves. So, arithmetic geometers, for example, the number theorists, they're trying to get more arithmetic theory on K3 surfaces, like they have arithmetic theory and elliptic curve. Okay, so let's go. When K called the field of complex numbers, then every complex K3 surface is simply connected. So this is another interesting point for topologists, because this is simply connected. So it is one of the building block of classification theory of simply connected four manifold. Well, okay, I always, I never miss why so named. Andre Bayu is first named so after Kummer, Keller, and Kodaira. So three mathematicians who had who made a great contribution to the study of this object. We have three Ks here. And the beautiful mountain K2 in Kashmir. So what is the next beautiful object after K2? It should be K3. That's quite, yeah, okay. So let me skip this fact about complex KC surfaces. Here, with the cut product, the second integral cohomology is an even unimodular lattice of signature 319. So it is unique up to isometry. So it is isomorphic to 3 copies of hyperbolic lattice and 2 copies of E8 lattice. This is negative definite here. And we have a notion Picard group or Néron-Severi group in this case. For KC surface case, these two groups are isomorphic. And this is a sublattice of this lattice, and it of length 0 through 20. And if X is projective, then this lattice is hyperbolic. And all KC surfaces are Keller, proven by CU. So Hartree decomposition holds for them. And here, automorphism of X acts faithfully on this cohomology lattice. And then a Torelli theorem, proven by Piatki, Shapiro, and Shafarevich, and Burns and Lapoport. Well, algebraic case, these are two persons, they proved, and Burns and Lapoport proved that for Keller Casey case. And by Torelli theorem, the automorphism group is isomorphic to the orthogonal group of Picard lattice, modulo -2 reflection subgroups of this orthogonal group. But this is not quite isomorphism. This isomorphic up to finiteness. This means that there is a map from this group to this quotient group with finite kernel and finite co-kernel. So if you really like to compute this group, then we have to compute this one first. And then the finite part can be handled in some other way. So for this purpose, Nikulin and Binberg, the expert on hyperbolic lattices, integral lattices, and so on, they classified necessary hyperbolic up to necessary extent the hyperbolic lattices. But this is not quite enough to prove to compute the automorphism group. So the automorphism group or the orthogonal group, well, in general, given any hyperbolic lattice, the computation of orthogonal group is not a trivial problem. Well, as you know, that Rick Borchard, one of his main work is how to compute this orthogonal group. But anyway, so here, may be computed using the combinatorics of a Leech lattice lambda. Lambda is an even negative definite lattice of rank 24 without any -2 root, without any -2 vector. Self-intersection -2. Well, there are exactly 24 unimodular negative definite even lattices of rank 24. So the Leech lattice is one of them, characterized by this property without any -2 root. And one can embed pick x. So given x, then you can compute pick x, and then you can embed this one inside this hyperbolic lattice of unimodular hyperbolic lattice of signature 125. Here this is 2. 2 means even. 1 is index of positivity, 25 is index of negativity. So this is isomorphic to the diaxom of hyperbolic lattice and Leech lattice. Well, about this, the combinatorics of Leech lattice and the geometry of this hyperbolic lattice or orthogonal group of this hyperbolic lattice is quite well understood. The best reference is Conway Sloan's book, Sphere Packing, lattices, groups, and sphere packing. So, using this information, we can derive some information on this group or orthogonal group here. And then in this way, by some geometric argument also, some standard K3 surfaces are computed. The automorphism groups are computed. So the generic Jacobian-Kummer surface case is computed here, and Kummer surface is product type, and Hessian of a cubic surface. So this Kummer surface of product type means that the Kummer surface is quotient of an abelian surface by an involution, and if the abelian surface is product of two elliptic curves, and in this case we call product type. So now, up to now here, I concentrate on how to compute the full automorphism group in the case automorphism group is infinite case. Now, let's think about the finite groups. So we are more interested in finite groups in some sense. Classify all finite groups G which may act on a K3 surface X defined over K is algebraic closed of any characteristic. And little bit minor problem is classify all finite groups G which may act on a K3 surface symplectically. Here symplectically means that here an automorphism is symplectic if and only if it preserves the global two form. It belongs to kernel lambda. Here lambda is the representation, automorphism group sending to general linear group of one-dimensional space. This is generated by global two form omega x. So if you pull back this two form, then it is another two form. So they differ by a scalar. So if this number is equal to 1, then the automorphism map is symplectic. So if every element is symplectic, then the group is symplectic. So in other words, this group preserves the symplectic structure of this K3 surface. Well, for this problem, Mukai gave complete answer. He classified all finite groups G which may act on a complex K3 surface symplectically. It turns out that such a group must be a subgroup of M23. This is Mathieu group of M24 with one point stabilizer, stabilizing 1 point. So this is a subgroup of symmetry group on 24 letters. So this group G can be characterized by this property. It should have at least 5 orbits on the set of 24 elements with respect to the permutation action. Well, Mukai's list consists of 80 groups with one group acting differently topologically. So with 81 topological types. These are subgroups of, among these 80 groups, there are 11 maximal ones. So each realized on an explicitly given K3 surface. So these are such groups. So this is a simple group L27. And this is another simple group A6. And then these are non-simple groups. So the maximum possible order is 960, which is obtained by Mathieu group M20. This is 4-point stabilizer, 4-point stabilizer of M20, stabilizer subgroup of M24. And probably, okay. Also, you can get different equations, but this is the original list of Mukai. And then, after Mukai classified all symplectic automorphism group, finite symplectic automorphism groups. Now the natural question is what kind of non-symplectic extensions of Mukai groups. So Kondo, he gave global bound for any finite group acting on a complex K3 surface X then G, the order of G must be bounded by 960 times 4. So this is the maximum possible symplectic part, and this is the maximum possible non-symplectic part. But this non-symplectic part order, this order depending on the group. So in this case, it is 4. But some other group, then it could be even 66. So kind of in between, what kind of extensions is not, but it's not an easy problem, but we have a global bound here. And also equality holds if and only if the group G and the surface X is completely characterized like this. And then you can take a similar question. For example, if you take A6, so if the finite group G contains A6, here A6 acts symplectically, and then the group G cannot exceed, the order cannot exceed the order of A6 times 4. And then the equality holds, then the surface X and the group G, and the action is uniquely determined. Well, Munkai's proof characterizes the representation of the group G. Here G is a finite group, finite subgroup of this full automorphism group, on the cohomology space. Here actually this is cohomology ring, but we don't use the ring structure here. Well, K3 surface has K3 surface is simply connected, so one-dimensional cohomology and three-dimensional cohomology both vanish. So zero-dimensional and two-dimensional and four-dimensional. So this is this is dimension 1, this is dimension 22, and this is dimension 1. So altogether it's 24-dimensional vector space. And compute the character. If you have a group action, then we need to compute character to analyze the group action. And the character is by definition is a trace of this action. But these are all even, so this is nothing but alternating sum of trace on each cohomology space. So by Lefschetz fixed point theorem, this is nothing but the Euler number of the set of fixed point. And then Nikulin, he classified, each automorphism G, and he showed that the set of fixed points are always finite, and the number of fixed points depends only on the order, and he classified like this. The pair is one of the following. If the order is 2, then always it has 8 fixed points. Order is 4, then always has 4 fixed points, like this. And then from this, this character is equal to the Euler number of the set of fixed point. And this, because this is zero-dimensional, and this is the number of points of this set. And this is equal to the functional value epsilon of the order. Here, the function epsilon is given by this. It's given number theoretic way. So if n is equal to 8, then this number can be computed as a 2. 7, then this number is 3. But this function describes the character of the 24-dimensional permutation representation of the multi-group M23. So this is the starting point of Munkai. And then using this, he did actually quite tricky group theoretic argument and also a geometric argument to show that the group is isomorphic to G prime, which is a subgroup of M23 with at least 5 orbits. Here, number of orbits correspond to the dimension of G invariant subspace. So G invariant subspace has dimension at least 5. So this each invariant subspace corresponds to invariant vector. So if you have an orbit, then each element inside the orbit corresponds to a basis vector. If you think of the 24-dimensional vector space, and then if you add up all these vectors, then this vector is invariant under the group action. So there are some alternative proofs of Munkai's theorem, Kondo, Xiao, but none of these proofs extend to the case of KC surfaces in positive characteristic. And there are examples in positive characteristic whose automorphism groups contain a finite symplectic subgroup not in Mukhai's list. Well, right after announcement of Mukhai's proof, it was 1985 in the Summer Institute in the United States. At that time, I was a student at University of Michigan, Ann Arbor. And then the people talking about the possible extension of positive characteristic case. But there are quite pretty but discouraging examples here. Thermoquartic surface. If you think of this surface in characteristic 3, I mean just a set of solutions in the algebraic clause of F3, and then the rank is 22 or 20, depending on the parity of the prime. So if P is equal to 3 modulo 4, then it's 22. And P equal to 1 modulo 4, then it's 20. And over the complex KC surface case, this is impossible, this number. 20 is maximum. But in positive characteristic, we have this kind of possibility. So in same equation, but in characteristic 3, it could have more lines. Yeah, this is quite natural. And then assume that in characteristic 3, then this example is known to these people. And this general unitary group of size 4 by 4 matrices, and F9, this is field of 9 elements, acts on the Hermitian form. This is sum of fourth powers is equal to, here x bar is the conjugate to x over F9. So this is Hermitian form over F9. So this general unitary group acts on this, live invariant, this Hermitian form. So this equation. So the projectivized special unitary group acts on X, but this group is simple. So always symplectic because symplectic group belongs to the kernel of the character map. But this group has order very big, 3 million. The complex case is at most 960, but it's over 300 million. So this example is quite pretty, but discouraging people, and they're showing that the problem is not quite easy. And character 5 and 7 and 11, we have similar examples. Here's the difficulties in positive characteristic. There's no Torelli theorem, and the presence of supersingular KC surface. Okay, over complex KC surface, this value can take up to 20 only, but in positive characteristic, it could be 22. Here, supersingular means, supersingular doesn't mean the surface is singular at all. The surface is smooth. Here, supersingular, this notion is same as the supersingular elliptic curve. So elliptic curve is always smooth, but the supersingular means really is a kind of extremal object. Super extremal object. So no natural unimodular lattice containing the Picard lattice. For complex KC surface, I mean this Picard lattice or narrow stability lattice is contained in the unimodular lattice, which is cohomology lattice here. And also, the one more difficulty is presence of wild automorphisms. Automorphisms or the power of the characteristic. And these automorphisms are always symplectic, always preserve the global 2 form, because in characteristic P, P's root of unity is always 1. Okay? So, at a fixed point, the action is unipotent, not necessarily linearizable. This is complete difference from the characteristic 0 case. Characteristic 0 case, we always linearize locally. So we need to overcome these difficulties. So the first is this. And for wild automorphisms, there is KCA surface with a wild automorphism only if characteristic P is less than or equal to 11. So for big characteristic, there is no such wild automorphism. And this bound is sharp. And for example, for abelian surfaces, there is no bound. And for rational surface, there is no bound. And in the proof, we use this equivariant sheaf cohomology. It runs so quickly. Yeah. Okay, and then let's go. All right. And then finally, we got the complete answer to the generalization of Mukai's result in positive characteristic. Let's give a finite symplectic group. Assume that G is tame. Otherwise, this means that the order is coprime to the characteristic. And either X or the minimal model of X mod G is not supersingular alternate invariant 1. This is a specific surface. Supersingular KCA surface with alternate invariant 1 is such as the single surface. It has no moduli. And both X, either X or its minimal model of X mod G is not isomorphic to such a specific surface, then we have the same list as Mukai. And if the negation of 2 is that both X and X, the minimal model of X mod G, are isomorphic to the surface, the supersingular KCA surface with alternate invariant 1. So both and the minimal are supersingular with alternate invariant 1. In this case, we classify all possible groups. There are exactly 27 exceptional groups. So the paper is rather long, about 45 pages, but this part consists of more than half. Here I use, Mukai use Mato representation on this rational vector space. Now I'm working on positive characteristic, but in positive characteristic we still have the field of characteristic 0. This is the analytic field. So I use atal cohomology ring here, atal cohomology group. So this one has still 24-dimensional vector space of characteristic over the field QL, which is characteristic 0. So, okay, so we proved that the G still, the action on this space is still Mathieu. But here, if G is wild, then left side fixed point theorem does not hold in general, because in this case, left side fixed point theorem is like nothing but the zero fixed point, the fixed locus is intersecting the diagonal transversally. But in positive characteristic, this is not. Yeah. So this is not always true. But still, we can show that the representation of G is Mathieu if G is tame. So most of our proof is just kind of following Mukai's line, but there are many difficulties. And as I mentioned, all of them came from the characteristic of positive characteristic property of positive characteristic geometry. So here I use crystalline cohomology, atal cohomology, and still I need to compute this G-invariant subspace. And this is equal to 2 if and only if the exceptional case. This part is hard and this part is easy. Okay, so I think the time is up, so let me skip. And here, in characteristic 11, this is the borderline. If characteristic bigger than 11, then there's no wild automorphism, so all groups are tame. So characteristic 11 case, wild and tame both exist, coexist. So we need to classify the wild case. The tame case is already contained in our previous work. So all finite wild groups are classified here. So one of these 5 groups. So here we use the elliptic vibration structure and so on. So okay, so I'll stop here.